protein hydrophobic bodies that get trapped in the interior, something like this, and that close off the channels that isolate ions on one side of the membrane from ions on another. Some of these proteins are so constructed that in the presence of an electric field, they will open, providing a channel which allows the ions to flow through in response to the electric field. And this is what happens when a nerve fires. So this is the structure that permits you to have nerves. And it's the ability of the membrane to trap just this kind of protein, of course, the existence of the protein, so that in the presence of in the absence of an electric field, it's a seal. In the presence of the electric field, it's porous and allows ions to come through, transferring electric charge and firing the nerve. So there are many reactions of that sort that can go on. The membrane elasticity is, of course, critical. If your membranes were to crystallize, you would be in deep trouble because they would be brittle. In fact, if the membrane is too weak, it would tear. So it's critical to life that this membrane has just the right mechanical properties. One of the things that controls those mechanical properties are a group of compounds that do get trapped within in the hydrophobic part of the membrane, and these are cholesterols. They become embedded in the bilayer and stiffen the membrane. And this is a very good thing. If you did not have these and some other chemicals that stiffen those membranes and control its elasticity, then the membrane would be too weak, it would tear, and you would be unable to survive. The problem is, of course, that you can't get too much of this, in which case the membrane becomes too stiff, and you're back to having problems. So that's, I think that's all I want to say about this. Is, of course, a very cursory introduction to biological materials. It gives you a sense of a couple of things. They are complex materials, very much like the other materials that we use for structural purposes and other things. They have very complex interactions, and those interactions, what they can do, what they do, is determined not by what's present, this is the aggregate of phosphorus and nitrogen and carbon and hydrogen, but by the precise structure of the material, the microstructures, which allows it to take on the shape and perform all of these very useful functions. Okay, with that, we're going to move away from the structure of materials. We're going to turn into their properties. It's useful to divide the property. A liquid crystal is a, suppose we take these, take just any organic molecule, like a little stick, okay? And we disorganize it so that these little sticks are liquid or they're floating around in a liquid. And then in some way or another, we either create the sticks so that they spontaneously align, or we use something like an electric field or something to make them align, so that all the sticks are lined up. Well, that's a liquid crystal. It's still in a way a liquid, but it has a crystalline pattern to it. And these have, I don't think we're not going to talk about those specifically in this course, but they do have many obvious functions. One of the most interesting was, if you probably haven't ever done welding, but if you do welding, one of the real problems in welding is that the light of the welding arc is sufficient to blind you. So you have to wear glasses. You have to be concerned that you might inadvertently turn on the torch when you don't have your glasses on and you can have eye damage. And it's really a very frequent problem with welders that they get eye damage from using welding torches. So over the years, there have been many efforts to come up with better ways of doing that. The people who solved that problem were at the Sandia Laboratory in Albuquerque. This was some years ago, and they were actually dealing with another problem. And the problem they were dealing with was classified at that time, which had to do with pilots who might find themselves engaged in a nuclear war. And would they be blinded by the nuclear explosions in the event of a nuclear war? So they came up, it was the most fantastic thing, with these glasses using liquid crystals that would respond to light and had such a fast time constant that you could turn these on just like my glasses, look at across the room. If you set off an explosion right there, they would instantly become dark and protect my eyes. And they now have some rather expensive but very useful welding goggles that use a simpler form of that principle and are very protective. So liquid crystals can have very, very useful properties. And it's only something like a liquid crystal because you do have a very loose arrangement of these things that can reorganize itself fast enough to serve that function. But the minute the light hits it, it instantly reorganizes itself and becomes opaque. Yeah, like transition. The transition, they work on a different principle. But it's in the transition glasses. These are, for example, you don't begin to have the time constant you need to light a welding torch and then go dark. Yeah, it's actually these are with a reversible precipitation reaction. At least they used to be. I'm sorry, I don't know exactly what you use now. The original ones were reversible precipitation. Yeah.
I'm just curious if maybe you can explain very short how that welding back works like these ones work.
It's an ordering of the. Inside, let's suppose you have a whole bunch of molecules in the form of tiny little rods. Okay. When you these are the original ones. I'm sorry, I can't speak exactly to the one because there are other ways of doing it. But you have a bunch of tiny little rods, and they are when they are randomly oriented, the light can easily go through. Right. But in response to a bright, remember light's an electromagnetic field. In response to the intense electromagnetic field, they will align themselves, and in the process of aligning themselves, they will absorb. So I go from I'm transparent to I absorb. And if you find a way of doing that that has a fast enough time constant, so that you can get that reorganization almost instantaneously, then you have a good welding glasses or defense against. In fact, people think of bringing them back now because there's a problem around with people shining laser beams at aircraft. And some question is whether the pilot should be wearing protective eyewear to address that problem. With all of these things, please take everything I tell you with a grain of salt because the technology advances very quickly. And if I tell you something I knew 25 years ago, I was done today, maybe completely different. But the basic principle is you must reorganize something in the interior of the glasses so that if they are not set on, the glass is transparent. When they are set on, it becomes opaque. Well, not really opaque, but transmits very little light. And originally, it was done with basically liquid crystals. Whether that's the most modern way of doing it, I just don't know. Okay. The first thing we're going to talk about are the thermochemical properties of materials. Materials respond to thermal stimuli, such as temperature. You heat the material up, something happens to it. Chemical stimuli, you bring it in contact with something that has a different chemical composition. You can get interdiffusion and change its composition. Environment, the environment can attack the material, can cause it to corrode or whatever. Electromagnetic stimuli, electrical or magnetic forces. And finally, they respond to mechanical stimuli, mechanical forces. We'll consider all four of these, but we'll take the first two together because they do kind of get tied up with one another and talk about the thermochemical properties of materials. Responses to thermal or chemical stimuli define thermochemical properties. In order to understand how materials respond to stimuli in general, or thermochemical stimuli in particular, remember that organizationally, there are two parts to a response. You have to consider what the material can do in response to a stimulus. It can do some things, it can't do others. And that's ultimately decided by thermodynamics. Thermodynamics tells us what materials want to do, what they're trying to do. But the fact that a system wants to change in a certain way doesn't mean that it actually can or will. There not only has to be a driving force to cause some change, there has to be a mechanism that brings that change about. And there has to be some time for that change to occur, as with the glasses we were just talking about. So you have to be concerned about the science of thermodynamics, which addresses what materials want to do, together with kinetics, which tells us what materials can do and how quickly that they can do them. So we're going to study thermodynamics, properties, equilibrium phase diagrams, kinetics, continuous processes such as heat and mass diffusion, and then discontinuous processes such as structural phase transformations. And finally, environmental interactions. We'll talk about wetting and catalysis briefly, and then about corrosion, oxidation of materials. Thermodynamics. Most entering engineering students, in my experience, are scared to death of thermodynamics. Largely, I think, because, frankly, much of the teaching of thermodynamics is absolutely awful. I took my first thermodynamics course in the summertime because I had to be stuck there in the summertime anyway, so I thought I'd take a course and get that requirement out of the way. In the mechanical engineering department, we spent the whole summer, half the summer worrying about heat transfers, and the other half of the summer trying to read the steam tables. I don't know if you've ever looked at the steam tables, but they're no fun. And I came away with the impression that this was the worst subject in the whole history of the world. And it was years later before I realized it's actually a very simple subject, very useful, and is perhaps the fundamental science of virtually everything we do. So let me try to tell you the easy part, and I'll let somebody else tell you how to read steam tables. I still don't know how. I did pass the course, however, fortunately. In thermodynamics, there are, well, 3 laws of thermodynamics. It's actually what they call the zero law. We don't need that. The first law of thermodynamics defines something that's called the internal energy of the system, and it tells us that internal energy is conserved. You've seen this before, I'm sure, that the change in energy is the sum of the work done and the heat transferred. The heat, frankly, is thermal work. You can call it that. But energy is conserved. If one material or one system gains energy, another system must lose it. The net sum of energy is constant, leaving aside nuclear processes. The second law of thermodynamics is where everything gets interesting. The second law of thermodynamics defines something called the entropy. Now, it's really unfortunate that it got called the entropy, because that confused everybody, and has ever since. What the entropy is time. There is a measure of time that is real, that is the universal time, if you want to. And what entropy is a measure of the degree to which a system has evolved. If you want, it's a measure of the age of that system, or the time with that system. In fact, in physics, you associate it with 3 different things. Evolutionary time, which is the most fundamental association, with heat. Finally, people like to talk about it in terms of information. There's been a huge controversy for decades over whether entropy is or is not destroyed in black holes, and I think we finally concluded that it isn't. But these 3 different things are actually very intimately tied up with one another, although superficially it doesn't look like they are. They really are, and I'll tell you how in just a minute. The important thing about the second law is that when a system is isolated, entropy can only increase. And any system is an isolated system when you include both it and its surroundings together. What this means is that time runs forward. This is the only law in all of physics that puts a direction on time. Every other law of physics is reversible. I can replace t by minus t and the equations look the same. The minute you get the entropy involved, all of a sudden t and minus t are not the same. T is associated with increasing entropy, minus t is associated with decreasing entropy. So it makes an awful lot of sense to say since the entropy goes with the time, that the entropy is the time, and we can measure it as such. Let me give you a little example. Suppose we begin with a really simple, what we call adiabatic system. Suppose I take some gas, I put it in a container which is thermally insulated so it doesn't interact with its environment, and I arrange to be able to do mechanical work on this system. And this is an experiment you can do in a laboratory. People have. It's a modification of the old original Joule experiment that you may have studied in elementary physics. But we now equip this with 2 mechanical devices. Since we've isolated this thing thermally, electronically, whatever, the only way we can change the state of the material that's in this little cavity is by doing mechanical work on it. But I've arranged 2 rather different devices to do that mechanical work. Here I have a piston. And we assume this piston can move back and forth, and if its contact with the walls is frictionless. So I can do work. I can do positive work by compressing the piston. I can do negative work by pulling the piston down. The second device I have in here is a paddle wheel. I can do work on the system by turning the paddle wheel. But interestingly, reversing the paddle wheel doesn't reverse the work. Whichever way I turn the paddle wheel, I do work on the system. So I have a device here in which I can do mechanical work reversibly with a frictionless piston or irreversibly with a paddle wheel. This is what I call an adiabatic system. An adiabatic system is just a system, the state of which I can only change by doing mechanical work. An isolated system is one example of an adiabatic system. If I take this and fix the piston and fix the paddle wheel, I can't change the state at all. That's what's called an isolated system. So this is an adiabatic system. Now let me do some experiments. Basically, what the second law of thermodynamics tells me, or the observation that leads to the second law of thermodynamics, is that I can change the state of the system by moving this piston. I can do work on the system by moving the paddle wheel. But the work done by moving the paddle wheel is irreversible. Once I stop the paddle wheel, I can sit here and wait as long as I want, and the system is not spontaneously going to turn the paddle wheel to do work on me. So this is irreversible work. Now let's suppose that we move the piston. Since it's frictionless, and I'll take the energy. Remember that the change in the energy of the system by moving the piston is just equal to the work that I've done. There's no PQ, just dW. So if I move the piston, I change the energy of the system. Moving the piston so that I decrease the volume will raise the energy. Moving the piston so I increase the volume will lower the energy. And as I push on the piston, I will generate a curve that looks something like this. It's reversible. I can go back and forth as often as I want, since the piston is frictionless, and that's a characteristic curve. If I now turn the paddle wheel changes the energy without changing the volume. So here I have what happens when I turn the paddle wheel. The energy goes straight up. The volume doesn't change. If I now turn the paddle wheel, let's say, to get up to here, and I then start moving the piston, what I will discover is I now ride the characteristic that's in the upper part of the figure. I never get back to this lower characteristic. Changing the paddle wheel has irreversibly changed the nature of the system. So I therefore find that all of the states that this little system can have are divisible into 3 types: the past, the present, and the future. If the current energy volume characteristic that I can ride by moving the piston is right here, then I know that any state below that has to be in the past. Because the only way I could get to one of those states would be for the system to turn the paddle wheel and do work on me, and that can't happen. So if this is where I am right now, and you say, well, what about this state? I can tell you unequivocally that that's in the past, that's gone. If that state was ever occupied, it was at some previous time, it will never come again. The states up here in the blue field, in the top right, are states that are in the future. I can get to any one of those states I want to. All I have to do is to figure out which characteristic it rides. Well, I'll just go to the volume of that state and turn the paddle wheel until I get there. The catch is that if I go to the future, I can never come back again. So this one little simple experiment, if you want, defines a clock and a time. The time is constant along any one of these characteristic curves of the reversible transformations I can generate by moving the piston. The future time consists of all states that are in the future envelope, that is, that require larger energy at given value of the volume. The past time is all the states in which I would have to decrease the energy at a given value of the volume. So I've defined a time, and I've defined a clock, because by just knowing which one of these characteristics I'm on, I know what my time is. Now, all I have to do now that I've defined time, and now that I know that these characteristic curves each signify constant times, I just have to put a number on it. I can call this the year 0, this the year 1, and so on. Or if I want, instead of using time, which I should have done, which saved a lot of confusion, I can invent a new term and call it entropy. I can say, let me assign a number to each one of these curves, make it nice and continuous. Turns out that's a preferred way to do it, but we concern us. Let me just assign a number to each one of these curves. Since these curves are continuous, since I can have an arbitrarily small amount of energy, these curves are spaced together as closely as I want them to be. Let me put a number that's a continuous variable, and let me call that number the entropy. And that, folks, is all it is. That's what entropy is. It's a measure of the time. It tells me what I can do in present time, what is past, and what is future. And that's what I've essentially said in this plot. Curves of constant entropy or curves of constant time. We can assign a numerical value of entropy to each curve such that S is a continuous variable. Every state of the system, characterized by E and V, has a particular value of the entropy, because every state sits on a particular curve. So S is continuous, so then I can write a function. I can say S, the value that I've assigned, is a function of E and V, because every single state has a value of the entropy. It measures the evolutionary time of the state. It can only increase because I can only add energy at constant volume. I can't take it back out again. And it divides the past, states with lower entropy, from the future, states with higher entropy. Well, I'll let you mull that over until, I guess not Monday. Monday's a holiday, right? So it'll be Wednesday that we meet next. And then we'll talk about, not only review this, but talk about how that becomes associated with heat, and that becomes associated with information. I'll tell you about that.